Hi everyone, welcome to Amazon ML Summer School and welcome to the part 2 of Sequential Learning, where would be focusing about how we can embed the context in which the words appear in a sentence to the vectorial representations of words. So till now you must have read about embedding some words which appear in textual format to a mathematical representation, either using classical methods which are based on counts on frequencies of words appearing like DF, or learning vectorial representations using some objective function and optimizing that objective function based on whether a word appears in neighborhood of other words in my corpus or not. But in all of those methods, if I change the context in which my word appears, the vector representation of the word is not going to change. Now, how to have the vector representation of my word dependent on the context? Why should we have it dependent on the context? Let's take an example of I sat by the river bank, I deposited money at the bank. Over here, both the words in the same textual format, BANK bank, have very different meanings. If I have the same vector representation of both the banks, my model is going to be confused about what does it mean. So for disambiguating these two banks which are textually same, I need to make their mathematical representations, which are vectors in our case, be different from each other so that my model, which is going to perform any task with that textual sentence or a document where it is having this word bank in the correct way, my model needs to distinguish between these two banks properly. How can we do that? By having some representation learner or some model or some function outputting a mathematical representation of this word dependent on not only this word but also the context in which that word appears. So it has to be a function of the word and also the context. It has to be adaptive to the context dependent on the context on which the word appears and get a different representation based on the context. How to do that? In the deep neural networks lecture, you must have gone through recurrent neural networks or long short term memory LSTM networks. Like each neural network was specifically helpful for different kind of data because of the inductive bias in that architecture. Like convolution neural networks is helpful in images because of its properties like being equivariant to translation or how we like to extract features from non-structured image pixels. In similar manner, for a textual data, you want to sequentially learn the information where networks like recurrent neural networks or LSTM is helpful. You might think that for making my output or making my word representation dependent on the context, I can use any f of x. The f of x can be a MLP, simple neural network, or a CNN, or a combination of things. But because recurrent neural networks or LSTMs have this inductive bias to perform better at textual data, which is a sequential data, and sequentially updating the information of future tokens of future words dependent on what was previously in the input. LSTM or RNNs might be well suited for making this function of f of x, which takes the context as well as the word to make the representation of that word. So we would be discussing a particular architecture which is called ELMO, using which we get vector representation of words which is dependent on the context. Now, what does it use? Suppose we have a sentence written over here. I want to embed each and every word and get a vector representation from it. It is in textual format. I would need to convert it into numbers first of all. How do we convert it into numbers? We have a simple lookup table For each and every character, over here, my tokens are characters. Okay. For each and every character, I would be having a particular embedding which would be randomly initialized. Those randomly initialized embeddings would be passed through a convolution neural network. Now, coming to the first part, for each and every character, I'm taking this for an example, but characters can also be other characters other than alphabets. Each and every character we look up in the embedding lookup table to see what is the representation of that particular character. Suppose we have our dimension embedding. Now, for each character, I have an R dimensional embedding. Suppose my word has multiple characters. Let's take for an example t number of characters. So I would be having t cross R dimensional matrix where each and every vector represents the R dimensional vector represents that particular character. I want to learn a transformation from this T cross R matrix to a lower dimensional compressed information, which I would be passing to the next layer of my Elmo architecture. What we use for that are convolutional neural networks. Now, this design of convolution networks where you have different sized kernels for the same input might look similar to an architecture popular in vision. I mean, not popular right now, but it was popular way back in 2014-16 called Inception Network, where we have convolutional kernels at different scales operating for the same input image or intermediate input. In our example over here, we can think that the three sized kernel is going to window over three characters in my word. Three characters in my word. So it can be intuitively understood as a trigram mathematical representation of a what a trigram does. We go on taking this with three kernel convolution and then a max pooling is applied. Suppose we have different scales. On having different scales, we can have different n grams depending on the kernel size. So I am trying to embed my word by having a learnable embedding for each and every character. And these embeddings would be randomly initialized. But as I train my whole architecture, these embeddings will also be learnable and optimized for the best outcome. We have these convolutional layers as a operator which is trying to get n gram representation of theirs. We do convolution, we get max pooling, then we concatenate all of them to pass into the bi-LSTM layers. We can have some transformation in between uh, to make the dimension less. The transformation can be a simple linear layer, or we can use some gating mechanism like highway networks. For now, to make the architecture simple, we would be skipping that transformation part, but just for the sake of completeness, I mentioned that. Now, first important part was I can embed any word because I have character level learning of embeddings over here. If a new word comes in, we would have the embeddings of those characters. We can pass through convolution neural network that word, and we will be getting those representations. So, a particular thing to be pointed out over here is that I can train my model on some training data set. On the test set, a new word can come in which was not present in my training corpus, but I would be getting a representation for that particular word too because of the design of my embedding of the word. So after we get those embeddings, we pass it through one layer of LSTM, which is a forward moving LSTM. Like the previous hidden state is transferred through some linear transformation to the next hidden state. The next one is backward language model. After we have the forward language model, we have the backward language model. Language model over here just means that we are doing next token prediction. Kind of, we get the hidden state from the previous time step and we use it to transfer information to the next time steps. So if we have embeddings going in it, we have a bi-LSTM layer, two layers of bi-LSTM, which is forward looking, two layers of back bi-LSTM, which is backward looking, and the final embeddings that come out from each and every time step for each and every word is the representation we learned using the Elmo method. Now these representations are going to be dependent on the context in which that particular word appears. That's the most interesting part. We were trying to figure out that how to make it dependent on the context, how we make it dependent on the context after we get the character level embeddings encoded through convolution neural networks. We pass it through two bi-LSTM layers, one forward looking and then one backward looking, because we want to learn that if we only knew the past tokens or past words, then what is my next word being represented as? But the words coming after that particular word which I'm trying to embed might also influence the context in which that word appears. So we need to also have a backward LST with the forward by LST, forward LST layer. So that's called, together we can call it a bi LST, which helps us encode the word representation, not only dependent on that particular word, but also in the context that that word appears. Now, these were the details about design of the Elmo architecture. It has convolutional layers, it has free embeddings of each and every character, it has the weights of those four LSTM layers, two forward looking, two backward looking. But how are these weights being learned? Now, the simple objective function in Elmo is the language modeling objective function, which is the MLE, which is the maximum likelihood estimate of the next word given the previous words in case of forward looking. And again the next one, but in case of backward looking, t plus 1 given, or let's say t given t plus 1 to the end. So this maximum likelihood estimation of next word prediction is used for training my Elmo language model. And as from the naming too, you can see it's a language model. The objective function is this, but for gaining this objective, you need to learn good vector representations which are dependent upon the context. And our goal of learning vector representations which depending upon the context is also achieved by training my Elmo language model. So this was Elmo language model on a high level and how it is helpful to us. Okay, now we need to look at what are some disadvantages in the recurrent neural networks and what do we need to do to get past those disadvantages. One of them is the long dependency I need to have for encoding any of my token in the time sequence. For encoding any of my token, I am getting input transferred from many of my past values. Now, input being transferred from many of my past values vanishes. The information starts fading a lot. It's kind of like a decaying problem. You do many multiplications, we are doing many matrix multiplications throughout, and it starts decaying. Let's observe how it does so. Now, for an example, if you see, I have the weight matrix's absolute value over here, the modulus of it, to just show how the decay happens. Over here, I have 10 tokens, and we are doing some repeated matrix multiplications, which is done in recurrent neural networks. Now you can see the information of the token at t equals to 1 decays as we embed it for any future time step, and the decay becomes worse while long distance we have to any future time step. Even if we are doing back propagation to update my weights, there would be a vanishing gradient problem because of the similar phenomena. Let's do backward pass. So on doing my backward pass through using the chain rule, I have some output from this. The output goes to my objective function. I want to minimize my objective function, my loss function. I would be taking gradient with respect to the weight over here as well. And for taking that gradient using chain rule, I will have to multiply many gradients, many gradients, and it will lead to a vanishing gradient problem. These two come as two modeling advantages, modeling disadvantages of recurrent neural networks. And another third disadvantage is that if we are getting connection or relationship between any two tokens, it's not a direct connection. The connection comes just because the previous token had a connection with it, and the previous token has a connection with it because the previous one has it, because the previous one has it. What I'm trying to say is the different tokens. Suppose I want to find relation between these two. The relation comes because we go through these intermediate relations, which is a chain of relations. There is no direct interaction being quantified. And also, other than these modeling problems, RNN would take time, so there is an efficiency problem as well. We need to operate on previous time steps for operating on the next time step, so we can only do this sequentially. We cannot operate on this time step t equals to 50 without operating on t equals to 49, 48, 46, because we need the output from these in this. We cannot parallelize the different operations taking at different time steps. So it's a bit inefficient too. So what all we want is if we can get direct relations between different tokens, if we can get rid of this sequential dependencies we have, so that we can parallelize things. Now we would be moving next to how or what architectures can help us get rid of these drawbacks of RNNs, and also take an example of a task where we use RNN and it also gives us, or even LSTM, it gives us another disadvantage specific for that kind of tasks. Okay. After that, we have discussed some disadvantages of RNN or these kind of sequential LSTM models too. We will be moving to encoder decoder architecture, a particular architecture design used in sequential learning, especially for tasks with a sequence to sequence. Sequence to sequence means where my input is a sequence and my expected output is also a sequence. Let's take for an example. I want to translate a sentence in some other language into English language. My input is a sentence, which is a sequence. My output is a sentence, which is a sequence. I want to summarize a story. I want to summarize a paragraph. My input is a bigger sequence. My output is a smaller sequence, ideally, or I want to answer questions. Now, these different tasks can have different objective functions, need to be trained on different kinds of data, but my input is a sequence and my output is a sequence. So, the architecture design or my modeling function design can be a bit similar. For all those kind of tasks, a particular architecture design called encoder decoder networks are usually useful. Now, how does encoder decoder network works is, as from the name you can decode The encoder is a function which would be helping us to encode my input sequence into a particular representation, which is called a context vector in the encoder decoder terminology. I take this representation, I give it to a decoder, and decoder helps me to generate another sequence by taking this context vector as input. Now, we have an example of a translation problem where we have a sentence in some language. We have an encoder. In our case, it would be a sequential network, a recurrent neural network. A recurrent neural network would be applying those matrix transformations, those activation functions sequentially to get a context vector. We can get a context vector by using the last hidden state, last time steps hidden state of the RNN, or we can try to aggregate all the different time steps hidden state in some manner by taking some transformation or by applying some activation function to get a context vector. For the sake of simplicity, let's take our context vector to the final timestamps hidden state right now. Now, that context vector would be summarizing my input sentence in some other language I have. What I want is I give this context vector to my decoder, and my decoder sequentially generates the same sentence but in English language. This is what I want. Now, how my decoder is going to generate this is token by token, token by token. We had a sentence which is a sequence of tokens. We had a sequential network as an encoder. The encoder gives me a context vector CT, let's say C capital T, the last one, hidden state. I give this context vector to my decoder. My decoder is going to take this context vector, go on to transfer the information, make the prediction of the first token in my output sequence, which is an English language sentence. We'll take this, we'll take the context vector, go to the next token in a similar manner. It will be generating the whole sentence by generating tokens one step at a time. The architecture is same as an RNN uses, take previous time steps, some context vector going over here. The main problem. My context vector is summarizing this whole input sentence. My decoder has no information of how this word in English language might relate to some other position or some other word in my input language. How much should this word's prediction, let's say this token's prediction, be influenced by some particular token in the previous language sentence? Everything was summarized, and then I gave my decoder that this is all the summary I know. Decode the final English language sentence. So you can observe some compression of information we do, some lost information, some lost granular connections between output tokens in my output sequence and the input tokens I have in my input sequence. And also, as you can see written over here, for short ones, it might work fine. because we have less compression, we have less sequential uh, decaying problem as well as the context vector might summarize everything for you. But if we have a lot of stuff, suppose we want to do some summarization, or we want to have translation of bigger paragraph or bigger corpus of text, what should we do in that case? If we can design something which helps my decoder look at different input tokens while it is generating the sequence in my output space, which is an English language sentence. At this point of time, it only looks back at the previous token in my output sentence only, or it can have information of my context vector because of the context vector being tra- uh, matrix multiplied and transferred step by step, step by step, step by step. How can we look back? Let's see. Attention. As the word might suggest you, we want to pay attention to different input tokens for different output tokens of mine. How much attention to pay to what token remains a question. How do we solve for this question? Let's take for an example. We have some sentence and we want to know how much each output token should be paying attention to another input token. We want a score quantified between each and every input token and each and every output token so that we can comment on how much relevance or how much attention pay to that previous token. These are my inputs. These are my outputs. What I want is for each of my output token, I would want a relation or a connection or a score, I would say, with each of my input tokens. And it remains same from these, from these, from these. Total of, if you say the input length is n1, the output length is n2, I want n1 cross n2 number of scores. And then I want to decide what to pay attention to, what to pay not attention to. How we can get these scores? Now, this becomes a question. How do we compute those scores? Those scores can be computed in multiple methods. First intuitive method that can come in our mind is we have S of t as the decoder hidden state at step t. We have H of I as encoder state at position I. what we would do, we can take a simple scoring function. The scoring function can be anything. We'd be scoring the relation between these two input output tokens represented as S of t and H of I, and then we can use softmax to normalize it, and then we would want to make a context vector again based on these weights. We use these weights and take weighted average of our encoder hidden state at every position for each and every time step t. That context vector which we had in encoder decoder architecture was one context vector C of capital T for the whole input sentence. Right now, what we have is for each and every decoder position, I have a context vector. How do I get that context vector? I get my relevance scores for that particular hidden state, decoder hidden state, with each and every input hid, hidden state. I get those scores. I take averaging of all my encoder hidden states to get that particular decoder context. Now, this brings a dependence. This brings the granularity of finding relationship with each and every input token. What remains a question is how do we score each and every output token with each and every input token? We can have multiple options. The first one can be a simplest thing you can think of. Let's take a linear combination of both of these vectors, my input hidden state, output hidden state at different positions, maybe. They can have different dimensions. I would project them into the same dimension by using my uh, transformation matrices W1 and W2. Then I just use a simple tanh activation function for some nonlinear operation I want to perform on them. And then I take a dot product with V transpose, which is a vector, which is again a learnable vector. This can be the simplest form. I want to find some relation between S and H. I do W1S plus W2H. I take a activation function operation on it to have some non-linearity as well. And then what I do, I take that this is a vector V transpose. I want to multiply this with the output of my simple one layer neural network, maybe, which takes S, which takes H, gets some output vector. I want its dot product with this vector V. Another thing we can do is we can simply take dot product between these two vectors S and H as well by trusting them that we don't need any other parameters. We can trust these vectors and their positions in their vector space to get the cosine similarity between them and comment on how much relevant these two things can be. Over here, we would need zero additional parameters. In additive attention, we were needing W1, W2, and V. Over here, we would not need any parameters. This is an advantage of this method. They can have different names, but they are just different mathematical functions replacing that score of S comma H. Another thing I can do is I can take a dot product, but with some tuning into it. Or we can call it, if we want to go into something more interesting, then we can call it an energy function. We have some weights. And I don't want to take a simple dot product between S and H, but I want to weigh different dimensions of S and H differently while taking this similarity between these two vectors. And how do I weight those two similarities depends upon this weights of this W. So I have a bit more control than freely taking cosine similarity between them. Again, we can see how it relates to the distance functions or the notion of distance and similarities, which we learned in unsupervised learning. The next option, which builds the heart of modern LLMs, is a scaled dot product. We would see that this idea gets extended in the attention is all you need paper. The score S of H is again being quantified by a dot product between S and H. We trust those two vectors to be very good at finding similarities between each other. But we are normalizing it by dividing by root of d. Why do we divide by this root of d? We would be observing why do we divide, otherwise what disadvantages it can have without division. But these are the different options. We can replace our score functions by some are traditional ones, some are the ones which form the foundation of modern LLMs. Now we saw for replacing the traditional encoder decoder architecture where my encoder summarizes whole of my sequence into one context vector. What we did was we tried to score each and every decoder hidden state of mine with my encoder hidden state with a concept called attention. How much attention to pay for different input tokens. We have different score functions to do that. Now, this was about one's kind of sequence attending to different kind of sequence to see how much is the relevance of that input for influencing my output of that particular hidden state. What if I have an input sequence and I want to attend to my own sequence? One word in an English language sentence, this cat cannot be a dog. I want to attend from my dog's tokens hidden state to each and every hidden state present in my input sequence only. If I can do that, it avoids the drawback which RNNs have of sequentially passing on information which decays the information. If I can attend to each and every token in my input sequence, I get a direct connection between each and every token, which was a drawback pointed out in RNNs. Now, how do I apply this idea or attending to input tokens itself? The idea is called self attention. What we want to do is we want to have some kind of matrix multiplication or dot product between each and every hidden state which each other hidden state of mine. We will also see how to do it efficiently, but first of all let's try to understand the concept behind it. So as you can see, if we have encoder decoder attention, what we are essentially doing is we are having some score of each and every output token. In our case, let's take it as the word in the output, the sentence written in French is the output, the sentence in English language is my source, is my input in this case. And consider it like a matrix where I get what is the relevance between this and this token. Let's take 1, comma 2, 1, comma 3, 1, comma 4. And I have the weight or the attention scores with me. Let's go to the second target token or word, and I have its attention scores with all the input tokens. Same for third, same for these. As I told, it's like n1 cross n2 number of scores. And a matrix formulation might be helpful for us to compute it, because what I essentially want is I have this vector. Let's take a d-dimensional vector. I have each of these vectors which are d-dimensional vectors. I want inner product of this vector with all of these vectors of mine. Let's say there are n1 number of vectors. I want this d-dimensional vector to be done inner product operation with each of these n1 number of d-dimensional vectors. This can be easily done by a matrix multiplication. And if we also parallelize across this, it can be done by matrix multiplication of two matrices. This was an example of encoder decoder attention. If we move to self attention, only difference is n1 is equal to n2 and the vectors are same. I take inner products between each of them. Now what's the catch is in the attention is all you need attention. We don't take direct inner product between the vectorial representations of each and every token. As we saw in encoder decoder attention, we have the hidden state of output space token, input space token. I take inner product between them to quantify my score. Here, let's take for an example, we have some embeddings for my output time steps, each and every token. I have some embeddings from my each and every input token. I want attention score between them. We would not take direct inner product, but we would take inner product of some transformation of them. Let's see what's that. Okay. I have a simple input sentence. I am happy. What we want to do is self attention. I want to take attention score between each and every token of mine with other tokens, including that token itself too. This is the self attention I want to do. I can have a scoring function to get the scores. What's that scoring function? The scoring function is we make three kind of entities: query, key, and value. I get a query vector corresponding to each and every token. I get a key vector corresponding to each and every token. And I get a value vector corresponding to each and every token. How do I get those vectors? I get those vectors by multiplying some weight matrices WQ, WK, WV respectively with my embeddings. I want a query vector. I want a query vector for my embedding x1. I would multiply by WQ. I want a key vector. I would multiply by WK. I want a value vector. I would multiply by WV. Now, what do these query, key, and value represent? What I want to do is I want to find out scores. Those attention scores are going to be found out by inner product or dot product between query and key vectors. How much is token I related to a token j is going to be found by qi into k transpose. We take the dot product between q1 and k1, we get a score. q1 k2 get a score, then q2 k1, q2 k2, q2 k3, then q3 k1. For each and every one as a query, I want to find out how is it related to others when they are keys. Let's take for an example. I have an input embedding xi. I multiply it by my wq to transform it into a query vector. I multiply it by wk to get a key vector. Intuitively, you can say that query vector says how am I going to be related or what information I would be needing from other key vectors. And key vector of this one would have the role of providing information when other tokens query to it. So when we get the score between qi and kj, it measures that relevance score, the attention score between qi and qj. Then those scores we have got are divided by root d. The reason for division is that we don't want our scores to have a very high variance. If my scores have a very high variance, my softmax can get some weird activations. We'll discuss it why. We have the root denormalized scaled scores. We take a softmax to get the attention weights. So what all we have been doing? We have the input embeddings. We have the input embeddings. We multiply it with a query vector, with a key vector, with a value vector. For the attention scoring, we use the query and key vectors and get dot products between them. The query and key vectors were found by multiplying with these WQ and WK matrices to project them onto same dimensions. And that dimension, let's say it's dk. Over here it's written dk is equal to 2. We would be projecting our embedding, which is of dimension 4, for an example, to dimension 2 by using these matrices. And we use these query and key vectors to get relevance or uh, those attention scores. Those attention scores are scaled down by dividing by root dk, and then they are normalized by using a softmax. Then we get those final attention scores between I comma j to make that matrix n comma n matrix. Now, what's the use of this value vector? After we have got those attention weights and we want to have output for each and every time step, how do we get that output? For any time step I, the output would be the those attention weighted average of the different value vectors. For any token I got it attention score it with itself and with other tokens by using its query and other tokens key vectors. I got those scores. I divided by root d. I applied softmax on it. I have some scores. I multiply those scalar scores with value vectors at each and every token with the corresponding value vectors to get my output. This is where value vector comes in. As you can see, the output 1 is the score into value vector 1, output the attention score second into value vector 2, the attention score third into value vector 3, and we get the final attention score. The final output vector we have, which is of d dimension again, because value vector was in d dimension. It's just weighted average of some vectors. The weights are my attention scores found by query and key vectors. That's what the attention is all you need is. Here's just an example of we get attention score between each and every token with each other token by using the query vector, the key vector. We take a softmax on the root divided form of it. We use these scores to average multiple vectors. Now this whole operation can be vectorized by matrix multiplication. You have been seeing these matrices, these multiplications again and again. Let's see how. I have a query vector, I have a key vector, I have a value vector. Over here, let's say I have two tokens. Embedding of token 1, this is embedding of token 2. I want a query for this, I want a query for this. I want a key for this, I want a key for this, I want a value for this, I want a value for this. I multiply with WQ to get a query vector. I have a query vector in a lower dimension for each and every token. I just have two tokens. I have a key vector for those two tokens. I have a value vector for those two tokens. Now these Q, K, and V have the query information for 2, key information 2, for value information for 2, and these are matrices of mine. If I do this operation, query key transpose, what I'm essentially doing is I'm getting an n cross n matrix where n is my number of tokens. In this case, token length is 2. I would get 2 cross 2 matrix having my attention score between each and every token with other token. And QK transpose, a matrix multiplication between two matrices, is going to get me, and that is why this operation can be parallelized using GPUs. RNNs were not able to be parallelized. This can be parallelized because we just need inner products between different vectors, which can be done using matrix multiplication. After we do this matrix multiplication, we divide by root decay. We take a softmax to normalize those scores. After we have normalized scores, we want to multiply those scores into a value vector. After I have a 2 cross 2 matrix, say 0.2, 0.8, 0.3, 8, 0.2, for an example. This is this part, my attention scores. I want it, my outputs O1, O2 to be the weighted average of my value vectors V1 and V2. What I would do is I have my V1, V2 vector, these two vector, together in this array will form a matrix. I multiplied with this. What this multiplication is going to do, it is going to take each and every element of my v1 vector, multiply with 0.2, add with 0.8 of the same indexed element of v2. This is what is going on. It is just attention score of this into v1 plus attention score of this into v2. This is what is linearly happening. I wanted weighted average of value vectors. I'm getting weighted average of value vectors as well using a matrix multiplication. This whole process can be parallelized. Only at the softmax is in between. And how do we get rid of this softmax has been the part of recent research for making this attention process most efficient for modern LLMs. But the foundation of modern LLMs being the attention mechanism used in attention is all you need paper is this, and that can be parallelized using matrix multiplication as you saw. We have a very interesting thing to discuss, which is why we apply with this root D. Let's discuss that too. Okay, if we take dot products between these vectors and we have layer norm in our architecture in transformer, we would be seeing in the next part of sequential learning, that is part 3. The normalization does is like a batch normalization. What it does is it tries to get the mean to 0 and tries to get variance to 1. Now for uh, this each and every component in my vector q1, my vector k1, these components would be having mean equal to 0 because of layer normalization and variance equal to 1. If we want to take a dot product between these two, we need to multiply these. Let's say we have in a dk dimensional space, we have two random vectors. We take a dot product between them. Let's take all different orthogonal bases to be independent random variables. I am multiplying all of these q1, k1 plus q2, k2, and so on. The mean is going to be 0. But what about the variance? As the number of additions increase, my variance is going to increase. And the number of additions would depend upon what is my dimension, the dimension in which I operate. So as my dimension increases, the variance, the variation in the QK transpose values, the score values I get, unnormalized score values increases a lot. There can be a case I have my means to be 0 and uh, let's take 64 dimension or 1632 dimension. Let's take, I can have values going from minus 32 of the inner products to plus 32. The inner products being, we have It can be as much negative as much as positive because of the free movement of different vectors randomly in an n-dimensional space. So let's say it goes to minus 32 over here, it goes to 32 over here. I do no scaling. I take a softmax. My softmax would spike up, spike down. I would be taking zero values, almost zero from some of the tokens. There is complete information loss from those tokens. Would I want to do that? No. I would want to have a smoother distribution to take some information from other tokens as well. That is why we divide by root decay. To decrease the variation or variance, the extremes we are going to get in our QK transpose values, we want to normalize it. And the more the dimension is, the more the variance is. So why we divide by root decay. Let's see it with an example. I have small d, d equals to 2. My raw QK inner products look like this. These inner products look like this. They look like well distributed. There is no too much of spiking up, it's spiking up. You can also see from the entropy, the uncertainty, more the uncertainty, there is less of one probability spiking up. If I have one probability spiking up, I'm not uncertain. I know about only one thing being the answer, the right answer. Let me increase d equals to 8. You can see few things spiking up. At d equals to 32, we have these QK values. I use softmax. Softmax spikes up only one value too much. Everything else gets zeros out. And when we divide by root d and then we use a softmax, because of the variance decreasing, my softmax is not so much spiked up. This also gives you insight about how softmax operation affects the probability distribution of mine. It's going to spike my probability distribution to be very non-smooth. That is why we also have a concept of something called as temperature in softmax. This is something you can uh, read to get more out of these insights we are discussing. Over here, the point is we want to divide by root d so that we don't have this kind of problem of just having one attention value very high, not attending to any other tokens. We don't want this. You can see as we go on increasing d, the spike goes on to be much more worse. To do not have that spike, we have this fix of dividing by root d. Now let's move to multi-head attention. Multi-head attention is simple. I want to have these attentions multiple times. Let's say 4 times. So I will need to have 4 different kind of query vectors for each token, 4 different kind of key vectors for each token, 4 different kind of value vectors for each token. And this each type is called one head, like H1, H2, H3, H4. They can carry different kinds of attention information. How much is this place, a place word, related to that place? How much of this word related to that place grammatically? Is there some grammatical connection, some semantic connection, or something else? This is what we call heads, kind of like tiling your query vectors multiple times to have different things to convey. If we have multiple heads, we will have multiple query vectors, multiple uh, key vectors, value vectors, and we will have multiple attention scores. We would be concatenating all of the uh, outputs I get by getting weighted average of value vectors. We would concatenate all of those. So if I had head equal to 1 and my dimension was 64, of q, k value. My output also comes out to be weighted average of the values vectors. So my output is also having 64 dimension. Now I have four heads and I want to have the same output. What would I do? Same dimensional output. What would I do? I would divide my 64 dimension into four dimensions, four different equal divisions, like 16 dimension. So if I have 16 dimensional four kind of queries, 16 dimensional four kind of keys, and then I have four kind of values, I get four kind of outputs to which are four heads output, which would be 16 dimensional. I would just concatenate all these 16 dimensions to get 64 dimension again. This is a simple concept which is used also while we implement this in PyTorch. Different heads can learn different things as we discussed, and attention is still evolving as we discussed. That getting rid of that softmax is something which is being researched and also tried in flash attention. And we have something called as Mamba, which uses the concepts of control systems and electrical engineering to make this attention mechanism much more like a state space. We have something called a state space in control systems and how we can translate and that analogy to the attention mechanism we are putting it over here. This was the end of part 2 of sequential learning. The next part would have the recent architectures like GPT for you, language modeling architectures for you, and how we assemble all these to form transformers. My colleague Ahmad will be teaching you in the part 3. Thank you for listening to this, and I hope this was insightful to you.